Yes. And that's why this is not a fair equating. It's a, I put the word effective there to kind of say ish, but yeah, the main thing I'm trying to do is show that they're comparable, but sort of not. And they maybe shouldn't be compared, I don't know, but I think that trying to compare things gives you more intuition for why we do it. And I claim that momentum is sort of a continuous version of mini batches, which is why I'm having you do this at all, is just so that you can see that they effectively accomplish a similar thing. Except with momentum, you get to take a step after every single pattern presentation. With mini batches, you don't, therefore momentum is better. Okay.
Do we do momentum with mini batch?
I have never seen momentum and mini batches combined, although there's no reason you couldn't. So that's an interesting thing. I'm sure some paper could study how to tune them together in order to do something, but I've never seen it happen.
So we either do momentum or mini batch?
Yeah,
Yes, okay.
we'll say that. You know, I take that back. I have seen momentum done on so when you use a neural net on a GPU machine, you're almost always going to use mini batches because they adjust the mini batch size such that every processor on the GPU is computing something. That way you're maxing out all of your processing power. So that effectively that's the main reason that they still use mini batches today, is because of GPUs. And if you were to throw a momentum behind that as well, that would probably make your program learn a little bit faster. There are people that have claimed that they've gotten out of local minima because of momentum as well. So it sort of has a smoothing effect. Imagine taking your error surface and smoothing it out a little bit. Now there's some local optima may go away. And that means you're, in theory, more likely to get to a global optimum. Here's the way my thesis advisor explained it. Imagine that you have a situation like this, where you're trying to get into the global optimum. If you just do stochastic gradient descent, imagine it going like this. And now you're stuck. That's bad. If you have a little momentum, well, now you'll roll down and the momentum will keep you going, and you roll over here, and then you'll end up getting down in here. Although, couldn't it just momentum you right up just there and then get you stuck there anyway? So momentum can do bad things, but it has been claimed that sometimes it does good things. And nobody knows if it always does good things, but it's something to do. That's kind of what momentum is. All right. So now you know what that's all about. Next I say download this code for C++ or Java. Let's see, I can't remember which I usually look at. I think we do C++ because the Java users can get it. It's easier than the C++ version. Okay. Next I want to show you, in fact, I'm going to open it a different way. What's this? Assignment 3, and the file's called preprocess. Okay, here's a folder. I have downloaded and unzipped that preprocess code into here. There are 2, 4, 6, 8 total files. There will only be 4 files if you download the Java version because I don't provide a CPP and a header file for each corresponding one. Okay, which order should we do? Let's start with the ones you know. In fact, let's start, oh, this is the interface one. Let's start with that. Let's open preprocess.h. Okay. This is kind of the base class for pre-processing operations. And if you had some data and you wanted to pre-process it, what would you do to your data? Well, the things you can do, I make inherit from this just because this provides some interface. And my pre-processing operations can be trained, like learning algorithms. But by train, I don't really mean what you're thinking. Wait till we look at some of them, and then I'll show you what I mean by train. But I have this transform method, which basically means take a vector and change it. And I have this untransformed method that means go back the other way. These are kind of the two methods you really need. And these other two things, actually, I'm going to come back and talk about them later. Okay, let's look at nomcat. And I'll open the CPP file. Here's what it does. Now, by the way, I need to clarify, nomcat is not a term that will be recognized outside of my classes. That's a name I gave this thing because I didn't know what to call it. In the Weka machine learning toolkit, they called it binarize, and that's a bad name for a bunch of reasons. It doesn't deal with only binary values, and therefore, I don't think that's okay. I could have called it one hotter. That seemed like a weird name. Not that nomcat isn't a weird name, but let's talk about what it is. Remember assignment 2, you used a one-hot representation with the MNIST data set. You might wish I had shown you this code before, but here's what it does. The transform function takes an input vector and gives an output vector. So for each thing in the input vector, it's going to ask a question: what is the number of values in that column? Let me put it this way. Suppose I have a matrix, and this matrix has a bunch of values in it, like your age and your, let's see, your shoe size and your hair color. And it has a bunch of values like 23, 11.5, blonde. That's me, by the way. I'm 23. Just kidding. 42, 7, black, etc. This is some data. This data is not suitable to be fed into a neural network. One of the reasons it's not is because this column here has a problem. The problem is that blonde and black don't really have any numerical ordering. And just so that we have enough to work with, let's suppose the next person is red, 12 and 3, there. Blonde, black, and red don't have any natural ordering, and you certainly don't want that case where if you're 49% confident that it's blonde, 2% that it's black, and 49% confident that it's red, you don't want to say, okay, well, on average, all the weight is on whichever one I said in the middle, black, and predict that it must be black, right? That would be a really bad prediction. So we want to convert this to a one-hot representation, and when we're done, the data should look like this instead. We would expect to see 23, 11.5, 1, 0, 0, 42, 7, 0, 1, 0, 12, 3, 0, 0, 1. Okay. And wouldn't it be nice if we just had a class all written that would just run through our matrix of data and would transform the columns as needed to do what we wanted to do? The answer is yes. So In the past, I've had students do all the pre-processing themselves. It's a good experience. You should probably write your own darn NOMCAT class. But I got tired of debugging those, so I finally wrote one that just works, and I'm giving it to you. I'm sorry for depriving you of important learning experiences. But let's look at this transform method and see how it works, just because if I'm going to write it for you, you at least have to look at it so that you can have some kind of experience for getting how this stuff works. Okay, if in size is not equal to, basically I'm checking my assumptions right here and throwing an exception if my assumptions fail. That's a good thing to do as a general programming practice. Always check your assumptions, write self-debugging code. Okay. Next thing, I'm going to resize my output vector so it's the right size, and then I'm going to run through all of my in vector. Okay? If the in vector has exactly one value, I just copy it straight over. That's a case that's really rare and shouldn't happen anyway. You'd never have a column with one possible value, right? If you do, something's weird, but everything comes up eventually, so I had to make sure this code could handle any case. Finally, the case that is very likely. Okay, we're going to run through all of the values, and we're going to set the target output to 0. That's basically saying we're going to come over here and make 3 zeros. Then we're going to go back if the value is actually known. Then we're going to go back and say, hey, the output value that we're actually talking about, which happens to be the index indicated by the input element, we need to set to a 1. So after we've made the correct number of zeros, then we fix that one and turn it into a 1. That's pretty straightforward code, isn't it? Or at least enough that you can, admittedly, there's a little bit of technical stuff going on in there, but for the most part, we're just saying for each element in the vector, find the ones that need to be expanded, expand them to that many zeros, and then set one of them to a 1. It's make a one-hot representation. Okay.
Could you go off this?
Sure.
Yeah, the train part?
Okay, let's talk about train. How do you train this thing? Here's what we do. For each column in the data set, we're going to see how many values are supported by that column. In my implementation, this one supports 0 values, which really means infinity values. I use the number 0 to mean infinity in my implementation. This column also has 0 values because it's continuous. This one supports 3 values because this is a nominal, also known as a categorical attribute. Okay, in a nominal or categorical attribute, there's some number of values that it can take on, and they're usually enumerated. So after I've loaded into memory, blonde is actually 0, black is 1, red is 2. And those numbers are indexes into where the one-hot value should be in the transform data. Yeah.
Does it remember what is what? Like make a matrix or an array somewhere that just gives it an order?
If you're using the loadarf function that I provided to you, then everything, after you've loaded something into arf format, the whole thing is just a big table of numbers. And so all it supports is, it's an array list of it's an array list of, or a vector in C++, of a double arrays. So each vector is a double array. And these are encoded with integer values inside those double vectors. Did I answer your question?
So you have this untransform method. Does that work to transform it back from a one-hot to like blonde, black, red? Because you have a lot of data. You might not remember which index corresponds to which category.
Okay. Yes, it does. Let's look at the I didn't finish looking at the train one. Let's look at train, then I'll go through untransform. So I think I'll get to it, but please repeat the question if I failed to address it. So here's what train does. For each column, we're just going to count the number of values. If it's less than 3, we set it to 1. Why is that? Oh, okay. That makes sense. So if it's continuous, or if there's only one value, or if there's 2, then I treat it like I'm just going to copy the value straight over. Why if there's 2? If there's only 2 values, it's binary, right? Male or female, or true or false, something like of that nature. Well, do you see that the problem we're trying to solve with the one-hot representation is not beneficial in that case? I mean, yes, you could have everything be a 0, 1 or a 1, 0, but you've really turned something with 2 possible values into having 2 columns, each with 2 possible values that are XOR, or they're the opposite of each other. That's not really helpful. So neural networks work just fine with binary values being treated as continuous values. Therefore, it's only if there are 3 or more values supported per categorical column that we even need to do any transformation at all. And therefore, if the number of total values is less than 3, then we're just going to say it's 1 for right now. And then when we come down here to transform it, we say, oh, if it's 1, let's just copy the value straight over. Otherwise, we're going to produce val's number, however many values it supports, that number of zeros. And then we're going to set the correct element to 1.